In this video, I'm going to show you how to generate the digital circuit when the state transition diagram is given. You're going to find that typically to find the state transition diagram is a little bit challenging depending the scenario, but once you have the state transition diagram, it's very easy to implement it in a digital circuit. So the one that you have here in the screen is a milli machine, and a milli machine is a state machine, okay, where the output of that circuit is a function of both the state and the inputs. So in this case, this state transition diagram has an input that we're going to call X and an output that we're going to call Z. And here, this is the way that we are going to express the input and the output in the different transitions. So let's suppose that we are in state A, and from state A we have an input 1 that is going to take our state and is going to send us to state B. If the input is a 0, we are going to stay in state A, and the output is going to be a 0. You don't really need to understand, okay, how this was obtained. That is going to be part of the lecture or another video. So, but if you are in B and your input is a 1, you're going to go to C, and if your input is 0, you're going to go to A. And this could be representing very different real-life applications, okay? That doesn't matter at this point, okay? Think on this as an abstraction, okay, where you have the states going from one to the other. If you are in C and your input is a 0, you're going to go to A with an output of 1. And if you get an input of 1, then you're going to go to D with an output of 0. If you are in state D and your input is a 0, you're going to go to A. And if your input is a 1, you're going to stay in D with an output of 0. So this is the way that you read the state transition diagram, and actually it's a little bit irrelevant at this point. What does A, B, C, and D represent? We don't even care at this point. What does the input represent or the output? We may even have multiple inputs and or multiple outputs. It doesn't really matter at this point, okay? The point is that we have a state transition diagram. Now, what we're going to do is we're going to take this and convert it into a table. And this is what we're going to call the state transition table. So basically, the table is going to look like this. It's going to have a current state, and the current state is going to be A, B, C, or D. Now, here we're going to have a next state. The next state is going to be the state that we are going to go depending on the input. So let's go back to the diagram so you can see how this table is generated. It's generated from the diagram. So you see A goes to B if input is 1. A stays in A if input is equal to 0. So if we go here, if input is 0, we stay in A. If input is 1, we go to B. And you can do the same for the other states. For example, if B for input 0 goes to A and for input 1 goes to C, look, how does it look like here? With input 0 goes to A, with input 1 goes to C. And you just continue doing the same for all the states. You put the current state, and in the other columns, you put the next state. Now, it's very important to see that we have to differentiate for x0 and x1. Why? Because since we have one input and it's one bit, there is two possibilities, 0 and 1, and you are not going to go to the next state, to the same next state necessarily, okay? You may go to one state for x0 and you may go 1 for x equal to 1 for another state. So that's what we are trying to capture here. Now, every time that we move to a different state, we have a different output, and that's what is here. Look, let's try A. Here in A is telling us for input 0 the output is 0. For input 1 the output is 0. And that's why we have 0, 0. Let's go to C, for example. If we go to C here, C is telling me for input 0, I have an output of 1. And for input 1, I have an output of 0. Look here. For input 0, we have a 1. For input 1, we have a 0. And so this is what we are going to be doing, okay? You're going to start from the state transition diagram. You're going to build the state transition table. It's basically the same information. There's nothing new, okay? From one to the other is exactly the same information, but it's easier to visualize it in a table, okay? Now, after we're done, we do that part, okay? We see that we have 4 states, A, B, C, and D. We need to assign a code, a binary code. How many digits is going to have the code? Well, in this case, because we have 4 states, we can cover the 4 states using only 2 digits, okay, 2 bits, I mean, because 2 to the 4 gives you 4. If the diagram originally had 6 states, then you will need 3 bits for the code, because 2 to the 3 gives you 8. In this case, 2 is enough. And I'm gonna call one of the digits or bits y1 and the other y0. And I'm gonna assign 0, 0 to A, 0, 1 to B, 1, 0 to C, and 1, 1 to D. And you're gonna say, why we assign it in that way? Well, just because, but there are different ways, okay? You can say, oh no, I want A to be 1, 1, B to be 1, 0, C to be 0, 1, and D to be 0, 0. You can assign these in different ways. And what is very interesting is that you may get better results with different assignations, okay? If you assign with different assignments, okay? If you assign this in a different way, the overall circuit may be a better version. And that is a topic that we're not going to cover in this class. And the reason we're not going to cover this topic is that in the old days it was very important to save, okay, as much as possible the gates, okay? We want to come with a minimized circuit. Right now, a lot of this is implemented in software, okay, in FPGAs, and we don't need to worry that much, okay, about how do we assign the states. Is a little bit it may be irrelevant, so we're not going to cover that, but you can find this in textbooks. Actually, in your sci book, you're going to see this. So let's just go with this assignment, and now what we're going to do next is take the table, okay, this table, the state transition table, and instead of putting A, B, C's, okay, we are going to substitute with the codes, okay, with the codes that we just assigned. So wherever we see an A, we're going to put a 0, 0, okay? Where there was a B, we're going to put a 0, 1, okay? Where there is a C, we're going to put a 1, 0. And when there is a D, we're going to put 1, 1. So this table is nothing else but the state transition table that we just covered, but with codes, okay? Now, up to this point, okay, this is the same process that you need to follow regardless what flip-flop you are going to use to implement. So these 3 steps that I covered, okay, are regardless the flip-flop. The next step that I'm going to cover, okay, this is step number 4, is what flip-flop are we going to use? So the following steps that you're going to see, they are dependent on the flip-flop that you choose. So I'm going to solve it first for JK and then for flip-flop D. For JK, we need to remember the truth table. This is the truth table, okay, the truth table of the flip-flop JK. And this is a transition table that was covered in another video, okay, and actually was part of one of your quizzes. So here it tells you what value we're going to get in Q plus or Q next, whatever symbol you want to use, for the different inputs in JK. This is like the opposite, okay? The way that we read this is, if the current state is 0 and the next state is 0, what are the inputs that you must have in J and K? And you see that we get 0 and X. If you are currently in 0 and you go to 1, what inputs do you need? 1 and X. Okay, if you are in 1 and you go to 0, you need an X and 1. And if you are in 1 and you want to go to 1, or stay in 1, basically you need X and 0. So we're gonna be using this table, okay, for the next step. Okay, I just put them here just to remind you that you need to memorize, at least for the exam, okay, these tables, okay? We're gonna use them. So now, what I have here is again the state transition table, okay? Transition table. This is the same table. But look what I'm gonna do first. I'm gonna take the table and I'm gonna focus first in Y0, okay, Y0. And because I'm gonna implement this with a flip-flop JK, I need to find the equations for J and K for the flip-flops. How many flip-flops? Well, it's gonna be one flip-flop per bit, okay, in the code. So the codes that we're using here are 2-bit codes, Y0 and Y1. So I'm gonna use one flip-flop for Y0 and one flip-flop for Y1. Okay, but this flip-flop has input, because it's a JK, has two inputs, has J0 and K0. So let's see, what are we gonna put there in those boxes? Okay, you see I have already some K maps. What are we gonna place in those maps? Look, the way that we're gonna do it is using the transition table for the flip-flop JK. This is the same table that I just showed you before, okay, the one here, okay, this one, okay, is the same that I have here. So we're gonna start with the first state, with the first symbol. We have a 0 here, okay, for this combination, and 0 will go to 0 when X is equal to 0, okay? Look, we are just focusing this in Y0. So this Y0 goes to this Y0, so this is Y0 next, when X is equal to 0, and this one goes to 1 when X is equal to 1. This one goes to 0 when X is equal to 0, and goes to 0 when X is equal to 1. This 0 goes to 0 when X is equal to 0, and goes to 1 when X is equal to 1. This 1 goes to 0 when X is equal to 0, goes to 1 when X is equal to 1. And this is just basically the codes from that we just put before. So, what we're going to do is the following. 0 to 0 means that J has a 0 and K is an X. Where are we going to put here? Well, because we are in this combination 0, 0, X 0, okay, the 0 goes here, and the X goes here, okay? Now, this 0 goes to a 1, okay? 0 goes to a 1. So 0 going to 1 implies that I need to put a 1 and an x. So I'm going to put a 1 and an x. Okay, where in those, why I'm writing those ones and x's in those cells? Because it's the one that corresponds to this combination. You see 0, 0, 1 is here, 0, 0, 1. And now let's go to the other one. 0, 1 is here. So 1 goes to 0. 1 goes to 0 implies x and 1. So I'm going to place an x and I'm going to place a 1 here. Okay, 1 goes to 0 is again x and 1. So I'm going to place an x here and a 1 here. Now, this is going to be a little tricky. 0 goes to 0. 0 goes to 0 means 0 and x. But where do I place them? Is not here. Is here. Is why? The 0 and the x goes here. Why? Because this is the combination 1, 0. The combination 1, 0. Remember, this is a truth table. This is a K-map. And remember that we don't follow exactly the same order in the K-map. So that's why it goes here. Now, this 0 goes to a 1. 0 going to a 1 implies 1 and x. So I'm going to put 1 and x. Finally, this 1 goes to 0. 1 going to 0 is x and 1. So I'm going to put x and 1. And then this 1 goes to 1. 1 going to 1 implies x and 0. So I'm going to put x in the j and 1 in the k. Sorry. 0, 0. This is a 0. Is 1 going to 1 is x and 0. Okay? So this is a 0, sorry. So we're done, okay, with the map. So we're going to simplify it. In this case, we collect these ones. We don't need to collect these, okay? So y0 is going to give me x. And I'm going to do this other one. I'm going to collect it like here. Let me just wait for me because I'm running out of battery in the computer. Let me just... Okay, sorry for that delay. Okay, so now K0 is gonna be, how do we collect here? Well, you see, we can collect this and this. Okay, I get quads. So this is x naught is this part, and this part is gonna be y1 naught. Now let's do the other one. Let's do y1. So y1 I have a 0, and this 0 goes to 0. So 0 going to 0 is 0x. So it's 0x. This 0 goes to 0, and that is 0x again. Now, this 0 goes to 0 is 0x again. And this 0 goes to 1, 0 going to 1 is 1x. Now this is a tricky one. 1 goes to 0. 1 goes to 0 is x1. But where do I place it? Here, x1. And 1 goes to 1. 1 goes to 1 is an x and a 0. X here, 0 here. Then we have 1 goes to 0. 1 goes to 0 is x and 1. X and 1 here. And then 1 goes to 1 is an x and a 0. X here and 0 here. If we simplify this, we can just group this, and that is gonna be x, y0, and we can group here like this. and this is going to be X naught. So with this, I just found, okay, the equations for the inputs of the flip-flops. Let's go to the next. The next part is the output, okay? If you remember in the state transition diagram, we have the outputs here. You see? The outputs depend on all of this. And how I'm gonna build this? Well, I go here, and this is my table. Okay, I'm gonna take that table and I'm gonna put it here. Okay, and you can double check this. I'm gonna put a 0 here and a 0 here and a 0 here, 0 here, 0 here, 0 here, 1 0. Why? I'm just following what you have here, what we have here, the truth table. So for this combination and for this x's, okay, you have this, and basically it's mapping this and this into the K map. Okay, you have done this several times, so it shouldn't be a problem. So how do I group this? Well, I just have an isolated one. So the output Z is going to be Y1, Y0 node, X naught. So now I have all the equations for the inputs of the flip-flops, and I have the equations for the output. If I go to the next page, these are all the equations, okay? The equations that I just found are all of these. And this is the circuit. For example, here, Y0, you can see that is connected directly to X. You can see that Y1, there is an AND of X and Y0. Y0 is coming from the flip-flop. Here, for K0, we have an X naught, so we have this X, okay, going through the naught. And then there is an OR here, okay? And then we have Y1 naught. And Y1 naught, if we just follow, is coming from Y1 naught here. The same if for here, J1 is X and Y0. And why? Because here we have an AND of X and Y0. And K1 is X naught. X naught is coming from this same signal if you follow it here. Okay, and finally the output is Y naught, that is coming from the flip-flop, okay? Then we have Y1, and then we have X naught, that is coming from the same inverter. And this is the way to design a finite state machine using flip-flops JK. The next video I'm going to show you how to do this with flip-flops D.